Hi, I am Sarah Shahri from Persist. In this talk, I present our work on almost fenceless persist ordering in Macro 2020. The emerging persistent memories or PM blur the gap between DRAM and disk. They provide DRAM-like performance with high density, non-volatility, and byte addressability. These properties make PM suitable for hosting recoverable data structures such as file systems and databases. Recoverable data structures need to guarantee failure atomicity. For example, consider this bank balance transfer scenario where Alice is transferring $20 to Bob. We expect that after the completion of this transfer, $20 is deducted from Alice's account and $20 is added to Bob's. So these updates need to be visible atomically in PM. However, without failure atomicity guarantee, the failure can happen in the middle of this money transfer, and $20 might be deducted from Alice's account, but Bob never receives the money. So some money is lost, and the question is how to achieve failure atomicity to avoid such scenarios. In order to provide such a guarantee, there are many techniques that can be applied, and one of the most common approaches is undo logging. In this approach, upon updating a persistent memory location in a transaction, the first step is to create and persist an undo log which contains the old value of the data. The next step is to update the data and then persist it. At the end, transaction is committed, which discards logs. If a failure happens in the middle of the transaction execution, log entries are used to recover the system to a consistent state. To ensure the correctness of this technique, these steps must happen in order that requires using fence instructions. Our goal is to provide the required ordering primitives more efficiently. In this work, we first highlight the inefficiencies of x86 memory persistency model to order a non-temporal update and its subsequent temporal updates, which result into enforcing unnecessary persist ordering. We then present Themis, a lightweight x86 extension that provides this ordering without using any fence instruction, and show that it can achieve 1.45x speedup over x86 memory persistency model on average. Here's a brief outline for the rest of this talk. First, I'm going to present some background details on memory persistency. Next, I will present x86 memory persistency model and its shortcomings. And then I present our work, Themis. And finally, I conclude my talk with some evaluation results of Themis. In this work, we assume that persistent memory is connected through the memory bus similar to DRAM. And in case of a failure, cores, caches, and DRAM will lose their data, but PM will not, and can be restored to a consistent state using recovery mechanisms. However, recovery relies on the underlying memory persistency model that constrains the order of writes to PM. There are many proposals offering different memory persistency models in academia and industry, but in this work, we are focusing on x86 memory persistency model as it is the only commercially available one. x86 memory persistency model provides two paths to PM. First, the non-temporal path, which bypasses the cache hierarchy and goes through the write combining buffer or WCB. This path is useful for updating memory locations that are not going to be accessed in near future, as they will not be cached. Consequently, this path is a perfect candidate for persisting undo log entries, as we access these memory locations only upon failure that rarely happens. This path exercises through issuing movement-like instructions and a subsequent expense to ensure it reaches PM. The second path, the temporal path, goes through the cache hierarchy and is useful for updating data that is accessed and modified frequently. Temporal path is exercised by issuing a flush instruction after modifying the data and a subsequent expense instruction to guarantee it reaches PM. However, as it is shown in the slide, these paths are not in sync. So if we plan to order two persistent updates across path to order, we have to use the sequence instruction to guarantee the order is preserved. This is a common pattern in undo logging, in which log is first persisted through the non-temporal path, and then data is modified and persisted through temporal path. Now the question is, how costly is the sequence instruction for providing such ordering? To answer this question, we eliminate these fences in the state-of-the-art undo logging, which violates the recovery requirements, but provides an estimation for sequence instruction overhead. We observe up to 2.68x speedup in linked list and 1.67x speedup on average after eliminating these sequence instructions. We established that using sequence instruction for enforcing this ordering is expensive, as only after a log reaches PM, core can proceed with modifying and persisting the data. Our goal is to find out how we can persist log before the data without an sequence. Let's first look at a real-world example in which Alice and Bob want to come back home after their vacation. Alice has the only key to their house and wants to take the shorter path. Bob plans to take the longer path to visit his parents before going home. Also, Bob does not want to wait on the road or at the door to get in their house. For this, they have two options. First, Alice can go home and then let Bob know that she has arrived and he can start his journey afterwards. In this case, the total time would be sum of Alice's and Bob's trip. The second and more efficient option is if they start their journey together. As a result, Bob can visit his parents while he is waiting for Alice to reach home. Since the path which Alice takes is shorter, there is a high chance that by the time Bob finishes his visit, he has already received the message and can continue his journey without any delay. The total time in this case is equal to Bob's trip. However, if Alice blows a tire, there must be some sort of communication link to ensure that Bob reaches home after Alice. So Alice can send a message and let Bob know about the incident. To sum up this analogy, we observe that option 1 enforces the required order by serializing the trip, and as a result is slow. In comparison, option 2 lets Alice and Bob to start their journey simultaneously and is faster than option 1. We highlight that x86 memory persistency model provides ordering primitives that can only make option 1 possible. As a result, we propose Themis, which is a x86 extension that can offer ordering similar to option 2. With this analogy in mind, we revisit the log data ordering example. Our goal is to eliminate the sequence instruction and let log and data to start their journey in temporal and non-temporal paths simultaneously. In the common case, the order is preserved and log will be persisted before the data. But Themis guarantees that this order is never violated by extending x86 memory persistency model in hardware. Themis is a lightweight x86 extension that provides efficient ordering semantics which guarantees persistent non-temporal updates reach PM before any subsequent temporal stores without any intervening fence. Let's look at Themis architecture. We extend x86 architecture by providing a communication link between temporal and non-temporal paths. Themis communicator propagates WCB updates to L1 write-back buffer or WBB, which is a buffer that maintains cache blocks that are going to be drained to L2. Using this communication link, Themis enforces the ordering only when it is required. To enforce the non-temporal to temporal ordering in Themis, we assume WCB to be a circular buffer with head and tail, and any update to head will be propagated to WBB through Themis communication link. As a result, WBB always has the latest head value, which is shown by head prime in the slide. Moreover, the current tail value of the WCB is appended to the incoming request to L1. And also, we extend L1 cache blocks to maintain this value, which we call WCB tail. This results into less than 1 kilobyte hardware overhead. When any cache block that belongs to PM is going to be drained to L2 because of cache replacement policy or flush instructions, Themis compares its WCB tail with head prime, and it can only be drained if head prime is larger than or equal to WCB tail. This means that any cache block that belongs to PM can be evicted from L1 only when all its prior non-temporal requests are persisted. Now let's see how Themis works in action. Using the log data example one more time. Let's assume a non-temporal request is already present in WCB and the recurrent value of head and tail are 1 and 2 respectively. First, the log is sent through the non-temporal path and consequently tail value for WCB is updated. Next, the current value of WCB tail, which is 3, is appended to the data request from core and is kept in the corresponding cache block in L1. Meanwhile, both entries in WCB will be drained and the head value will be updated. This update is propagated to WBB, so head prime would change to 3. Data then is flushed, and as a result, the WCB tail is compared against head prime. Since 3 is equal to 3, data can safely be evicted, as all its prior non-temporal requests that have been in WCB are persisted and order is preserved without any overhead. In the same example, if only one entry in WCB is drained, the value of head prime would be 2. And upon the eviction of data, because of flush instruction, since 2 is not larger than or equal to 3, data cannot be drained to L2. So its eviction from L1 has to be delayed until all its prior non-temporal requests are persisted. To conclude this example, in both cases, Themis enforces the log data order, and in common case, it is faster than using an expensive fence instruction in baseline x86 memory persistency model. Here's a brief overview of the experimental setup that we used to evaluate Themis. We used Gen5 simulator in full system mode, and more details on this are available in paper. We use a set of different benchmarks, including some simple data structures, tree-based data structures, TATP, and TPCC. We evaluate 3 different configurations. First, x86 memory persistency model as baseline. Second, Themis. And third, ideal. For the ideal configuration, we ran the code with removed sfence instructions on the baseline hardware. Although this violates the persistency guarantees, it shows the upper bound on what Themis can achieve. In this graph, I'm showing the speedup of Themis and ideal over baseline for different benchmarks. We observed up to 1.87x speedup in PC and 1.45x speedup on average. Moreover, this graph shows the gap between Themis and ideal is very small, which indicates that in most cases, the ordering is preserved without any significant performance loss. We also studied the effect of transaction size on performance improvement that can be achieved by Themis. This graph shows the speedup of Themis over baseline for different transaction sizes. As it is shown in all benchmarks, with higher transaction size, we observe higher performance. This is because the frequency of fences that can be removed with Themis increases. In other words, Themis improvements are higher with larger transactions. To conclude my talk, we showed that x86 memory persistency model offers two paths to PM, and we can only use expensive fence instructions to order updates across paths. We then showed our proposed extension, Themis, provides implicit ordering guarantees without using an intervening fence instruction that achieves 1.45x speedup over x86 memory persistency model on average. Thank you for joining our talk.